So, algorithms, recursive algorithms, and the definition is quite simple. It's just an algorithm that is calculates its value, does a calculation using previous values. And that's exactly what strong induction is. That's exactly what recursion is. And so let me start off right away with an example. And the first one is calculating a factorial. So factorials. Let's remember a factorial. Let me remind you, that is 1 times 2. 2 times 3 all the way up to n, and the previous one is n minus 1. I'm saying that because this tells me now how to calculate n factorial. This is just n minus 1 factorial. Okay, so here let me right away give you the algorithm, and then you see, we can discuss a little bit why it's recursive. So the procedure, so okay, I'm gonna do this again. So procedure, let's call it factorial. Why is it doing this? Factorial, and it just applies to a single element n, non-negative integer, say. Now, typical, of course, we have seen this for induction and for recursion, you have to start somewhere. And so this is always very often done with something like a class like if, and then if n is 1, that's the first case that you want to do, return a value. So in other words, you don't do any calculation in the initial step. So if n is 1, you just give the answer. Why is it? Then return 1, because that's what 1 factorial is. Okay. So and with if then we have done, if you're not in the original case, then you do something else. So we are in the else. Okay. So else. What you return then, well, okay, it's what we said here. The factorial of n is n times the factorial of n minus 1. Okay, so let's see what happens if I want to calculate using this thing. What is a factorial? I'm going to write factorial of 3. Okay. So what is this? Okay, what does the algorithm does? Okay, it puts n equal to 3, right? Then it's going to check is n equal to 1. No, it's not. So we go to the else loop, and then it says, okay, what you have to calculate now, fact3 is equal to 3. What is this? 3 times factorial of 3 minus 1, 2. Now the problem is we don't know fact2, so he's going to calculate fact2 now. So fact2, so n is 2. If n is equal to 1, no, that's not the case, so it has to do something else. What does the algorithm tell you to do? Well, it says it's equal to 2 times the factorial of 1. So now we have to calculate the factorial of 1. Right? So he's postponing the actual calculation. He's going backwards, tracing back what it is. Fact 1. So now n is 1. But this points me exactly in this class, right? So now I know that the answer is just 1. So this is 1. Now, once I know this, I can go back here and say, okay, this was 2 times 1, this is equal to 2. And once I know this, I can go back and here and say this was 3 times 2, this is equal to 6. Okay, so you see how it goes all the way back to the beginning stage and then comes back. So it's kind of a go down and up kind of movement that it makes. Okay, this is kind of a cute one, but there are more important ones. So for instance, the calculation of the GCD. So a recursive algorithm for calculating the GCD. GCDs are sometimes very important things to do. In particular, for instance, in cryptography, very often we want to make sure that the GCD of 2 elements is 1. That's very often what we want. How does it work? Well, it uses the fact that, so we're going to calculate this, the procedure, and for simplicity, let's always put the smaller one first. Okay. Of course, if they are equal, then the GCD is just the element itself. So I guess we should therefore write it this way. Okay. what we do, okay. So what the algorithm says is you create a division. That means you divide B by A, so you have a quotient and a remainder. And the remainder is, of course, the thing that tells me, that's where I am. Yeah, I'm gonna let's stick to this case here, okay. So this is my remainder, okay. And then the statement, the theorem, let's go look back to this previous chapter, says that the GCD of AB is the same as the GCD of R and A. I write it in this order because A is now the bigger, of course, right? That's exactly what we made it to be. And what is now the point is, at some point your remainder it's getting smaller and smaller. So at some point it has to become 0. It's the only way that it can be, right? If you look at this here. So once the 0, so if R is 0, then A is the GCD. Of course, we have renamed A and B, right? That it's not original A anymore. So let's see how this works in a procedure. It's clearer if I write it this way, okay? So the procedure, let's go just GCD. So it's GCD of A and B with A less than B. Now, okay, this is that tells me that we should stop if R is 0. In other words, this, look at what I'm trying to say here. Perhaps I should not write it this way. I should say if the first element is 0, then the second element is a GCD. So we're going to test the first element. If A is 0, then return. Let's think about what we have to return. So I'm saving a little bit of time. So if A is 0, so this, as I said, is the basic step. If A is 0, then we know what the GCD is. It is the second element, B. This is simply because the GCD of 0 and B is always B. Because the GCD, the greatest common divisor, anything divides 0, and of course the biggest divisor of B is B itself. Okay? All right. So what is the meat of the thing now? What is the else part? Else, return. Let's see what we have to do. Well, okay. Well, we have to now take the GCD of this thing. Now, what is R? Okay, R, we can write R. R is the remainder of dividing B mod A, and that is denoted by this function. So this is a function, right? This with two arguments, B and A, and it gives you the remainder of B mod A. This is something from modular arithmetic, okay? So what we calculate is, this is the R here, right? So this is B mod A, okay? And what is then, the new element is A. And that's it. So at the end, it will give you the GCD. So let's do very quickly. Let's do the GCD of, say, 4 and 6. We know, of course, that it's going to be 2. But let's see what the algorithm does. Okay, A is 4 and B is 6. So is A 0? No. So what you have to do then, it says it's a GCD of, now you take 6 mod 4 and 4. Now what is 6 mod 4? So we have to write 6 as, that's 1 times 4 plus 2. So this is actually, the remainder is 2. So this is the GCD of 2 and 4. Okay, so what is that? Okay, we go, it's a recursive thing, means that the procedure or the algorithm or the subroutine, whatever you call it, is calling itself, but with smaller values. Of course, if it would call itself with the same value, then you're in a loop, right? Then it's a loop and it will never get out of there. Okay, so what is happening now? Okay, so I have to write 4, we have to do the division here, that is 2 times 2 plus 0. So this is the GCD of this first element, remember, is this here, is B mod A, so this is the 0 here, okay, is 0, and then 2. Now we are in the situation that we can, in this situation here, that we stop, this is going to stop by algorithm right away, because it says if A is 0, then return B, return 2. And so at this point, it knows what the GCD is, okay? Another very important algorithm is modular exponentiation. And this is the following problem. So you have, it's calculating this thing. So now we have three numbers, b, n, and m. M should be at least 2. B is often assumed to be a remainder mod m, so let's take for simplicity b between, well, 0 and m, but 0 doesn't really make sense much here. And n is some power exponent, okay? Okay, there are two ways we can solve this. B to the n, you can recursively define as b to the n minus 1. So we can say b to the n is just bn minus 1 times b. Sure. But that means that we're going to have to then calculate bn minus 1 and so on. So we're going to have to do n steps to do this kind of recursive calculation. This is a smarter thing to do. bn is this. Let's assume n is even, and we'll adjust, minor adjustment when n is out. Let's look at this. This is true, right? N divided by 2, if the exponent of the power of a power is the product of the exponents, which is n. What happens is we have to take a square, sure, but this is a much smaller element, much smaller power now. Okay. What happens if n is odd? Well, let's quickly figure that one out. Well, let's subtract 1, square it. Now what is the result? Is b to the n minus 1, so I have to still multiply with b. So this is the two steps that we're going to do. This is, at the moment, the modular has nothing to do with it yet. But why is this not something, why we are talking about modular exponentiation? Well, if we would carry this out, say with b is 10 and n is 15, 10 to the 15, well, that's easy. Let's say b is 9 and n is 15. That is a huge calculation. The numbers are getting huge, right? Or say, for instance, if b is 9 and n is 213. 9 to the 213 is a number with about 200 digits. Good luck writing that number down, okay? But if you do modular arithmetic, let's say if we do this, so this would be 9 to the 213. I'm not going to calculate this, right? But if you do this, say, mod 40, then each calculation, you know that this is a number that's between 0 and 40, right? Because that's what modular arithmetic does. It gives you the number mod 40, the remainder mod 40. It's 0 up to 39, basically. And so you can keep numbers small, and that is why modular exponentiation is an important technique. So I'll say one more at the end, but let's look now at the actual procedure. So the procedure is, so I'll call it modular exponent. Let me write it in caps because otherwise. Modular exponentiation. Let me write it mod exp. And it applies to b, n, and m. Three integers which I already told you what they are. Okay. So what does it do? Well, again, it has to start somewhere, and the easiest start is the smallest power, n is n 0 here, right? Because n to the 0 is 1. So it doesn't even depend on b. We don't even have to think here. So if n is 1, then return, if n is 0, then return 1. Right, so let me fill it in. If n is 1, then return. No, if n is 0, sorry, then return 1. Okay. Else. So that's where we're gonna do our. Now we have to assume two cases. So let's again else. If n is even, then we do one thing, and then if n is odd, we do another. If n even, what do we do then? Then, this is a weird word, then, but it's there, okay. Then what do we do? Well, we calculate, we do mod exp, we calculate this number. What is that? That is the mod m. Now we're going to do, sorry, all this is now going to be mod m, right? So we're going to do this mod m. Well, mod m, let me write it perhaps in capitals also. Okay, mod exponentiation, what do? We do b, n over 2, and the modulus is still the same. B and M stay the same. It's the exponent n that has been halved. Now we have to square this. So we square this. But if we square a number that is smaller than m, it's going to be at most m squared. So we're going to still take the mod m here of it. We want to keep this number small. That's the whole goal. Throughout this calculation, the numbers that appear should never be bigger than, say, m squared or something, or perhaps m cubed. Okay? But relatively small. Okay, so this is n even, else, if n is even, else, well, then we know that n is odd, and then what we do then? Else return, yeah, sorry, then return, I should have put this here, else return, what are we going to return? Well, we have to do this one, okay? So what is this? Well, that is the mod exp. We now take, the exponent is going to be n minus 1 divided by 2. That is then again a number, that the correct number. We could have also written this as n2 floor. Okay. M, we have to square this. We have to multiply with b and then take the mod m again to keep it small. And that's it. Okay. So you could do this now in an example. I'm going to leave this for the homeworks where they ask you to explicitly do all the various steps. What are the various calculations that this algorithm has to do when you apply it to it? Okay, I'm going to jump to a more important one. No, not more important, this is an important one. Another important one is the merge sort. Merge sort. We talked about sorting in the previous video. I hope you watched that video. It's important, otherwise some things that I'm going to say you might not understand properly what I'm saying here. Sorting is an important algorithm because it allows, once a list is sorted, you can do much quicker, like a search in it. Otherwise, searches within an unsorted list are horrible. So what we normally do is, if we have a database, Google has its database of all key terms or search words. It's going to first alphabetize it, and then it's going to start searching it. Okay. So the merge sort, how does it work? Well, the sorting algorithms, we discussed one in the previous video, and so that was insertion sort, I think. I forget now which one I did. I think I did insertion sort. So insertion sort, and we analyze it, and we say it is about the complexity is n squared. Okay, that sounds not bad, but it is bad because if these databases could be something like let's say 100 million, which is not too big to. There's still a big database, but the square of 100 million, that is a tremendous big number. That is 10,000 billion. Okay, that is the 10 trillion. That's huge amounts. Okay. Okay, so what is the merge sort do? I'm going to do it on an let's do an example. So the list I'm thinking of is, let's say, Q, D, A, C, B. No, let's take here P, and I do B here. Okay, I'm going to take a list of 2, 4, 6. No, I want to do 5 elements. Okay, let me get rid of this C. Okay, that's just a very simple list. Okay, so let me give you the algorithm, because the algorithm is quite simple. Okay, and it's recursive. So the recursive version is merge sort. Okay, so what is the algorithm? So the procedure is merge sort. So okay, procedure is M sort. I'm going to write it M sort, otherwise I have to write too much. Let me write capitals because otherwise it's M sort, merge sort, okay. And it is applied to a list, and the list we will call the numbers that we enumerate the list as A1 up to AN. So the N is the size of the list. Okay, this is pseudocode. Again, we actually have to implement that. You have to do a little bit more fine-tuning, right? You have to declare the variable L to be a list, and and so on. But that's not what we concern about ourselves. Okay, so what it does? Well, here is and I'll explain, when we discuss this thing, you will see why this is somehow, it basically skips the initial step, because the initial step, let's think what the initial step is. Well, if n is bigger than 1, so n equals 1, what is the sorted list consists of one element? The list itself, there's only one element, right? So that's what that's why we don't need to do anything here. Okay, so if n is 1, then don't do anything, then then L is just L. Otherwise do this, else do this, but it's better to do it this way. Okay, what does it do? Well, the first thing it does is it says take half the list and split the list in two sublists. So this would be A1 up to AM, and L2 would be AM plus 1 up to AM. Okay, so if we do this here, so it said n is 5, so m would be 2, right? So this is where with the two list splits, this would be L1 and this would be L2. Okay? And what it's going to do now is going to sort each of these two lists separately and then put them together. Now, that putting together it requires another procedure that I call merge. I'm going to quickly discuss it, but that's not really the important procedure here. So I'm going to discuss it, but then we're going to go away from it. So procedure is merge. And what it does is it takes two lists, but now these lists are ordered lists. So we have much more information, and that's why this is not going to be such a complex algorithm. So we have two ordered lists, and so for instance, this is not the case. QD and APB are not ordered lists, right? But at some point they will be ordered, and then it's going to put these two lists together. So, and what does it do? What does it do? Sorry. This is not, by the way, not recursive. It's just straightforward. And I'm not going to even write down the pseudocode of it. I'm going to tell you how it works. So, on an example, suppose L1 is the list, say, C, F, Q, and L2 is the list A, D, E, X, Y. Okay, so how does it work? Well, it's going to create a list L. And how does it build L? It is very simple. At each moment, it's going to look at the first two elements of its list, the two lists, the first two elements. So this is A and C. Which one is the smaller? A. So you put that first and then delete it. And you repeat the process. Now it's C and D. Which is the smaller? C. Put it in your new list L as the next element and delete it. Now we look at the two smallest elements are D and F. So D is the smallest, so you put it there and delete it. E is going to be the smaller of the two, so you put it there and delete it. Then comes F, okay, you delete it, and now we have Q and X. Q is the smaller, delete it. This list is empty. What is happening here? Well, it means that everything that comes here has to be at the end of it. And it's already sorted, so I just concatenate. I just put it at the back. Okay, so that's how it works. It's very efficient. And so what's the complexity of this thing? Well, n, right? Because we basically run to the n, where n is the sum of the, so n is the sum of the lengths. Right? Because at each time we take one of the elements. We built a list of n elements. In this case it was 8 elements. But using a list from 3 and 5 elements. It doesn't matter how many, it didn't matter how big the lists were, right? The procedure was simple. Always look at the first element. And then if it's the smallest, take it away and move it to the sorted list. Okay. So the complexity is n. Keep that in mind when we talk about complexity of the merge sort algorithm. But I'm going to now do away with this one. We know how it works. And in the book it's described in pseudocode how it actually works. So what is going to happen here? So what is now my new list? Remember, my procedure has to give me a sorted list, and it says the sorted list is the following thing. You merge, which was the procedure I just erased, the sorted list M sort L1, because remember, this is an answer of my algorithm, right? M sort is an algorithm that produces a sorted list. It has an input, an unsorted list, but its answer comes out to be a sorted list. Okay, so this is a sorted list. And the same is true for this one. Okay, and that's it. That's how the algorithm works. Now let's do this on an example, on this example here that we had. Okay, so the original list was, so let me write it this way. I want to calculate M sort of the list Q, D, A, P, B. Okay, let's do these various steps. So n here, we start with n equals 5, and so m is equal to 2. Right, and this is what we are. And then we create the two lists, kind of half, we split it, in other words, we split the original list in two parts, right? The first part and the second part, which means basically here. So this is L1 and this is L2. And then, what is M sort? Well, it is the merge. Now you do M sort of L1, which is QD, and you do M sort of APB, and then you merge them. And we know how the merge works. But the program cannot do that yet because it has to still calculate M sort QD. So what is M sort QD? Let me give me a little bit space that I can fill it in. Yeah, M sort QD. What is that? Okay, so in this case, n is 2, right? And so my m will be 1. So this is how I'm going to split my list now. This is going to be my new L1 and new L2. So M sort is going to be merging, right? I'm applying again this thing here. L, this list is going to be the merge of M sort of the first part of the list. So M sort L1, which is just Q, M sort of L2, which is just D. But notice that we had this, this procedure only does something if the list is at least 2 elements. Because we argued if the list is 1 element, it is sorted. In other words, the algorithm says, yeah, but this is just Q and this is just D. And now I have to merge them. And remember, the merging is take the smallest of the both, that is this one, and erase it. And then whatever is left, put it there, because there's only one left. So this is now calculated. Now what about M sort of APB? It will have to work a little bit more because n is 3 and m is now going to be 1. So it's creating again two lists, this list and this list. So it's going to merge M sort of the first part of the list, which is just A, and M sort of the second part of the list, which is a little bit longer, it's PB. This one we know is A, so nothing to be done, but we have to still calculate M sort of PB. Again, n is 2 here, so m is 1, right? Here, I hope you're following here. I'm dividing the list into equal parts in this case, because it's even, so this is that. And that is now we merge, we M sort the first part of the list, which is just P, we M sort the second part of the list, which is B. But these are lists of length 1, so they are already sorted. And now we have to merge them, and merging again, we take the smallest, that's B, and then we put the rest, if there's nothing left, there, so BP. So we have calculated this to be BP. Now we have to still merge this, but this is not a recursive algorithm. So let's just quickly do this. Look at what the smallest of the both is. This is A, so put that first. Now you have an empty list, so put whatever remains of the second list, put it there. Okay, so we have sorted this now. Okay, so where are we? This we have calculated is A, B, P. Of course it's A, B, P, we know that, right? But we are following the algorithm. We're not thinking about it. We pretend to be stupid and only know this much. And then M sort QD, we had that, and that was DQ, right? So this is DQ. And now we have to merge, which is again, as I said, nothing to do with recursion here. Take the smallest element, A. Now look at the smallest element, that is B. Now look at the smallest element, that is D. Now look at the smallest element, that's P. And now we have an empty list, so put whatever there. And there we are, A, B, D, P, Q. So let's calculate the complexity of this algorithm. So let's see what happens. And I'm going to explain this using a very special value of 2. You saw that if you take some value like 5 or something, the lists are kind of a little bit askew, right? One list is a bit smaller than the other, so it's a little bit awkward. It's easiest if we take a pure power of 2, because we keep dividing by 2, we'll always have powers of 2. So we start with one list of size 2k, okay? And then we divide that list basically in 2 equal parts, right? That is what this thing says, right? We divide the list in 2 equal parts. So the next step, we will have 2 lists of size. Well, now the size is half of this size, which is just that. Each of these 2 lists I'm going to have to be treated again, and each of these 2 lists will be divided in 2. So we're going to have in altogether 4 lists of what size, and each of these are now half of this size. So n is now 2k minus 2. Okay, and then we're going to have each of these 4 lists going to be subdivided. Then we're going to have 8 lists, and they all will have size 2k minus 3. So let's look a little bit at the pattern here, and I hope it's so. These are powers of 2 as well, right? This is 2 squared. This is 2 to the power of 1. And look at these coefficients here. Look at the exponent: 3 minus 3, 2 minus 2, 1 minus 1. Of course, actually here this is 2 to the 0, k to minus 0. Okay, so in general, after I subdivisions, we're going to have 2 to the I lists of size. Well, we just take k minus I. Correct? Okay. And so how long does this go? Well, it goes until each of these lists here, until n is equal to 1, right? This will happen exactly if I is equal to k. And then we have 2 to the k, which is n, many lists, right? So after keep splitting, at the end we have one lists, right? Okay, so at each stage, what happens here? Let's look at this particular stage. Well, we have these 2 I lists, 2 to the I lists, and they have this size. Now, they come in pairs, right? And one of these pairs here, so one of these pairs, L1 and L2, they're gonna, we have sorted them, and then we have to merge them. Now, so in other words, 2 of these lists have to be merged. And how many steps does it require to merge 2 lists? It was the total size, right? So in other words, to make it simple, merging them requires 2 to the to the k minus I. Why am I saying I? 2 to the k minus I, right? When we merge a list with another list of the same size, what we do is we take we just run to both of these lists. So we're going to have this many steps, comparisons that we have to do. So this is the number of steps we have to do, and for each of these lists, and there are 2 I of them. So what we're going to do is for the I and the I step, we're going to have 2 I times. We're going to do well, let's not write O anymore, but let's fin. We're doing now O calculations, right? So this is so the complexity of merge of M sort is what? Well, it's a complexity, right? Well, we have 2 I lists that have to be merged, and this is the number of comparisons that requires them to merge, and each of them has to be merged, so that's 2 I of them. And then we have to do this for I going from 0 to k. Okay, so but what does this mean? Let's from I going from 1 to k, not perhaps. Well, let's work out what this number is. Well, 2 I times 2 I, so summation I from 1 to k, 2 to the k. But if you add k times this same number, what you get? K times that number, right? That's just because it's each time the same number. You're not doing anything there. So this is the complexity. It's about, well, I should always say about, right? About this many steps that we have to do. Now, what does this mean? So n is 2 to the k. That means that the log 2 of n is k. So this is approximately log 2, but we in computer science we assume that the log is the log 2. By the way, the log 2 of n is the same as the O of the log 10 of n. So in some sense, when we talk about complexity, it doesn't matter what the base of the logarithm is. Okay, so this is log n and to the k just n. So this is the complexity of m sort, where remember the complexity of the other sorting algorithms that we have seen previously was n squared. Now you say that's not a big deal. It is a big deal. Suppose you're sorting a list, say, of size 2 to the, let's say, 2, oh, what happened? 2 to the, to the 50. That is a pretty big list, okay, a big database. Well, let me perhaps instead of base 2, let me base. It's easier to think for us in base 10, so let me say it that way. So suppose you have, let's say, 10 to the 10 database entries, and now you want to sort them. Well, if you have to run a regular algorithm, then n squared is 10 to the 10 to the power 2, that's 10 to the power 20. That's now already a much bigger number. And this is a huge number. This, if you have to do this many steps, it would take way too long to do this. Okay? What is then, let's compare with n of log n, and as I said, since I'm talking about O, it doesn't matter which logarithm it takes, so I'm going to take log 10 here. So that is 10 to the 10. And what's log 10 of this number? So log n is just the exponent 10, right? So this is 10 to the 10 times 10. That is just 10 to the power 11. That is way smaller than this thing. It's just 10 times bigger than the original list, which is kind of remarkable, right? You have this huge list, and you have to, in order for you to sort it, you really have to do 10 times as many steps as the list is long, which doesn't sound something that would be the case if you would have to just naively start doing this. Okay, so one more thing that I want to discuss very quickly is iterative versus recursive. Now, recursive algorithms are very powerful, and for instance, this sort list is a recursive algorithm, and it's a very powerful algorithm, but very often they also require quite a lot of calculation. So I'm going to give you an example here. So any recursively defined function can be computed with recursive algorithm. I'm just going to do this for a particular function here, fn. I'm going to define it this way. Now, of course, this can only make sense if n is bigger than 2, so I have to tell you what happens f0. Well, let's take f0. Let's take f0 equal to 0 and f1 equal to 1. Okay, remember we have to initialize it. And now we have a recursive defined function, and this function has a name. It's called the Fibonacci sequence, after an Italian mathematician that first discussed this sequence. It's a very important sequence. It appears a lot in mathematics, in nature even. Let's look at some of the values of that. So f0 is 0, and this is 1. So this is f0, this is f1, right? What is the next one? Well, f2 is the sum of the two, so this is 1. And so f3 is the sum of the previous 2, so that is 2. And now we take the sum of these two, that is 3. Sum of these two, that is 5. Sum of these two is 8. Sum of these two is 13. And this way we can build the whole sequence, okay? Okay, so let me give now the iterative versus the recursive. I haven't told you what the iterative is, so let's go give you first a recursive definition, a recursive algorithm. So procedure, let's call it fib. So fib of n, and as I said, this is for this particular recursively defined function, but what I'm saying here works for any recursively defined function. Namely, what you do, well, you have to deal with the initial cases. So if n is 0, then return 0, else if n is 1, sorry, I'm not writing it because otherwise I have to then return 1, else. So I'm dismissing the first two cases because there are two now, that's why I need to do this a little bit more work. So if n is 0, then return 0, because that's what it's supposed to be here, right? Else, if n is 1, then return 1, else. So now we are in a situation that we can use the recursive definition. Here we go. Fib of n is just fib of n minus 1 plus fib of n minus 2. And that's the calculation. Okay. But for instance, if it has to calculate, let's say, F4 and F5, let's think about it. It has to if it calculates fib 5, it has to calculate fib 4 and fib 3. Okay. Now, to calculate fib 4, it says, okay, for fib 4, I need, that is fib 3 plus fib 2, so I have to calculate those. So it does that. Okay, so fib 3, it's going to take a while, right? So it says fib 2 plus fib 1. Oh, I know what fib 1 is. That is 1, right? Because that's, remember, this is now, whenever we n is 0 and n is 1, we actually know what it is. It doesn't have to do anything anymore. But I still have to calculate fib 2. So fib 2 is fib 1 plus fib 0. Ah, I know what both are. This is 1 and this is 0. So fib 2 is 1. So if fib 2 is 1, then fib 2 plus 1, that is, what am I saying? It's 2, okay? But, okay, so just to, and so now you can see how it goes, right? I'm not going to work the whole thing. But this is what the program does, right? So it says, okay, I have to calculate fib 4 and I have to calculate fib 3. This is the calculation for fib 4. But in the calculation for fib 4, it needs fib 3 and fib 2. Now, at this end, he's also calculating fib 3, but he doesn't know that he's already calculated in the other side. So he has to calculate it again, right? The program doesn't know these things. I mean, it follows its steps. It might have done this step before, but it doesn't know that anymore. It doesn't keep track of that, okay? So, in other words, it's not that it just has to break down each time one less and one less, but it has to keep doing this each time. So for the calculation of fib 3, he has to calculate fib 2 and fib 1. Now, in the calculation of fib 4, fib 2 occurs, but it doesn't know that it has already calculated it here, so it has to calculate it again. So you see, a lot of calculation has to go, this program has to run for a long time, no, relatively long time, to actually get to fib 5. Therefore, what's the iterative one? Iterative says, okay, we do it the way that we do it we build up the sequence. We build it up from this bottom. And I'm not going to write it down because it's not recursive, so I'll leave it to you to read it, the pseudocode for the algorithm. But the algorithm, the following is very simple. It says, okay, at any point, a given point, you take the first, the last two elements, you add them up, and that becomes your new element. So in other words, you at some point you have an x and y, that's for instance 3 and 5, and then you're going to define new x and y, that's going to be the x and y, that is what is going to be this pair. Okay, so the x is now becoming 5, and the y is now going 3 plus 5. Okay, and you keep doing this, so this is now 5, 8. So the new xy, so again, we define a new x. So this squiggle thing means this is the calculation that the algorithm does. So it says now, okay, 5, 8. 8 becomes the first element, and 8 plus 5 becomes the second element. And you keep doing this, and so it keeps track of in other words, it keeps track of the two consecutive elements, and at any time it does know now what the fib of any number is. You just have to keep track of it. Let me skip the actual implementation, which is kind of nice and simple. It's much quicker. But if you look at it, it's a little bit uglier. It's not so compact. Look how compact these recursive algorithms are. They're like 2-3 lines, whereas the iterative in this particular case is not much less, but more. But it's kind of almost double as many lines. And so, iterative can be faster, but it is often more ugly, and it has its disadvantages. There's for instance, the merge sort cannot be done iteratively, because iteratively it will be n squared. So in this particular case, you go much faster. Okay, that's all I want to say, and then the rest is in the exercises.